You know, every time something moves, whether it's a car, a planet, or even just you walking across the room, it's actually telling a story. A story of where it's been, how fast it was going, and where it's headed. Today, we're going to learn how to read that story using the really powerful language of physics. But first, let's start with a little thought experiment. Imagine you had to describe a whole journey. I mean the entire story. Every single stop, start, and turn. But here's the catch, you can't use a single word. How on earth would you do it? Believe it or not, the answer is lines. Yeah, it sounds almost too simple, right? But a few carefully drawn lines on a graph can tell a richer, more precise story of motion than a whole paragraph of text ever could. We're going to see how these lines aren't just boring data, they're a complete narrative. Okay, so to really get a handle on this, let's follow one simple story. A bike ride across town. Our cyclist, they're going to be our main character. We'll track their every move and watch how this visual story just unfolds. First things first, the most basic question you can ask is, how fast is our cyclist going? Well, that's speed. It's simply the distance they travel divided by the time it takes to get there. So, if they cover, say, 10 meters in 2 seconds, their speed is 5 meters per second. It's that number you see on a speedometer. Simple enough. But here's where the story gets a really crucial layer of detail. If I just tell you the cyclist is going 5 meters per second, you don't really know where they're going, do you? Are they heading towards the park, away from it? That's where velocity comes in. Velocity is speed with a destination. So here's the key difference. Speed just tells you how fast, but velocity tells you how fast and where to. Saying 5 meters per second, that's a speed. But saying 5 meters per second east, now that's a velocity. You can think of velocity as speed with a built-in GPS. And this little distinction, it is absolutely vital for everything from air traffic control to navigating a spacecraft. All right, now that we have our key terms down, let's get back to telling our story without words. It's time to actually start drawing the trip. So this right here is our canvas, a distance time graph. Look, on the vertical axis, we've got the distance our cyclist has traveled from their starting point. And on the horizontal axis, we have time just ticking by. Every single point on this graph is a specific moment in their journey, and the line connecting them, well, that's the story itself. So, what is this story actually telling us? Well, it turns out the shape of the line is everything. By learning to read these shapes, we can basically become motion detectives, figuring out the entire journey from just a single glance. Okay, now this is where it gets really interesting. This is how we decode the plot. See that steep upward line? That shows our cyclists covering a lot of ground in a short time. They're moving fast, maybe down a clear street. And what about this flat horizontal line right here? They've stopped. The distance isn't changing, even as time marches on. They must be at a red light. Then, the shallower line means they're moving again, but slower, at a steady pace. And if the line curves, that's a plot twist. Their speed is changing. Our cyclist is either speeding up, accelerating, or hitting the brakes. Reading the general story is great, but the real power, the real magic of these graphs is that we can pull exact numbers right off the page. This shows us exactly how to find the speed. It's all about the gradient, or, the slope of the line. Come on, let's do it together. So, step 1, pick any straight section. Got one? Okay. Step 2, find the rise. That's how far up the line goes, the distance they traveled. Step 3, find the run. That's how far across it goes, the time it took. And finally, step 4, you just divide that rise by the run. Distance divided by time, and boom, you've just calculated the cyclist's exact speed for that part of the trip. And hey, there's actually another type of graph that tells the story a little differently, a speed-time graph. We're not going to dive deep into that one today, but here's a powerful secret it holds. The area underneath the line on that graph, that gives you the total distance traveled. It's another amazing tool that engineers and physicists use all the time to analyze really complex motion. So far, we've talked about a bike ride, right? Motion that we can control. We saw our cyclist choose when to accelerate. But what about an acceleration that isn't a choice? One that's always there, this constant, invisible story of motion being written on everything around us all the time. Yeah, forget the cyclists for a moment. What happens when you just let go of an apple or your keys? They don't just move, they accelerate. Their speed actually increases every single moment they fall, and this happens in a very specific, incredibly consistent way. This number, this is what governs that whole story, 9.8 meters per second squared. It's one of the most fundamental numbers on our planet, the acceleration due to gravity. What this means is that for every single second an object is falling, its speed increases by 9.8 meters per second. It's this constant, invisible rhythm of Earth's gravity, writing its signature on every single falling object, from a raindrop to a skydiver. So we've seen that motion is a story, told in lines, speed, and direction, from a simple bike ride to the universal pull of gravity. Which really leads to one final thought. If a graph can map out a single trip so perfectly, what would the distance time graph of your entire day look like? I mean, think of all the flat lines when you're still, the gentle slopes when you're walking, the steep lines of driving, and all the little curves in between. You're writing a story of motion every single second. What story did you write today?